Properties of substances are largely dependent on the bonds holding the material together. A chemical bond occurs when atoms or ions are strongly attracted to each other. Ionic bonds involve the transfer of electrons and the subsequent electrostatic attractions. For example, let's say you're an atom and you give one of your electrons away to another atom. When you give one of your electrons away, you have a net positive charge. The atom that took your electron now has a net negative charge, and because opposites attract, the two of you then tend to stick together, and we call that sticking an ionic bond. Ionic bonds happen between metals and nonmetals, or more generally, cations and anions. Covalent bonds involve the sharing of electrons between two atoms. Let's say you're an atom and you are short an electron in your valence shell, and I'm an atom and I'm short an electron in my valence shell. But if I contribute one electron and you contribute one, then we can share those electrons and maybe both have a complete octet in our valence shell. And that sharing of electrons we call a covalent bond. Covalent bonds occur between nonmetallic atoms. Metallic bonds have each metal atom bonded to several neighboring atoms. The important part about a metallic bond is that the bonding electrons, namely the valence electrons, are free to move throughout the material. That is not true in covalent compounds, typically, with covalent bonds or with ionic compounds. That gives metals some unique properties that ionic and covalent substances don't have. Lewis symbols show only the valence electrons, that is, the ones that are involved in bonding. Carbon, for example, has an electron configuration that ends in 2s2, 2p2. That's a total of 4 valence electrons. Those 4 valence electrons are oriented like so around the symbol for carbon, and there are basically 4 regions that we can put these electrons: top, bottom, left, and right. So that when we write the Lewis symbol for nitrogen, which ends with 2s2, 2p3, that's a total of 5 valence electrons, we orient them like so: top, bottom, left, right, and then we have to double up somewhere with that 5th electron. And it doesn't matter where we double up, but we do. Then with sulfur, which has 6 valence electrons, we write the Lewis symbol like so: top, bottom, left, right, double up somewhere else. The octet rule says that atoms want 8 valence electrons. If we can personify atoms, atoms tend to want 8 valence electrons in their outer shell. There are several exceptions to this, which is a topic for later. Of course, the octet rule should be fairly easy to remember, since a musical octave consists of 8 regular notes: octopus, 8 tentacles, octagon, 8 sides. With transition metal ions, the electrons lost first come from the subshell with the largest value of N. For example, nickel has an electron configuration that ends with 4s2, 3d8. The nickel 2 ion has lost 2 electrons, and it's very easy to look at that 8 and reduce it to a 6, and that would be wrong, because the electrons that are lost first come from the subshell with the largest value of N. For the nickel 3 ion, then we start pulling from those d orbitals, and the nickel 3 ion looks like that. To review with transition metals, you might remember from an earlier lesson long time ago, and these are the elements that have only one s electron in their valence shell. Another mnemonic is that one right there. You notice that we've got an in the middle, and then we've got an arm on the left and an arm on the right, and those elements on the periodic table that have only a single s electron in their valence shell are these 6 right here. These are the notable ones, where the is this part right here in the middle. Ruthenium and rhodium and then there's a space. These also have a single s electron in their valence shell, and so do those. So that's kind of useful to keep in mind when you are figuring out what the electron configuration is for these atoms and also the ions of those atoms. Recall that polyatomic ions are groups of atoms that stay together and have a net charge. For example, the nitrate ion and the acetate ion. You will note that their atoms are held together by covalent bonds. You can see that for these two polyatomic ions, all the atoms are nonmetals. And that's true generally for polyatomic ions. And we discussed earlier that nonmetallic atoms are held to each other typically by covalent bonds. Final thoughts on introduction to bonding. Bonds are strong coulombic, i.e. electrostatic, interactions between particles. Valence electrons are the focus of attention when discussing bonding because they are on the exterior of the atom and influence the type and strength of the bond between particles. 2. Ionic bonds result from transferred valence electrons. The resulting ions are attracted to each other. Covalent bonds occur when atoms share valence electrons. Metallic bonding occurs between the atoms of metals. The structure of metals can be visualized as a regular lattice of metal cations in a sea of delocalized valence electrons.